Hello everyone, welcome to our TIGRE Exploring Enceladus presentation by the Engineer Your World team for CEASE 2024. Our objective is to design a mission to explore Enceladus, one of Saturn's icy moons. We aim to study Enceladus extensively by analyzing its surface material and subsurface ocean liquid. TIGRE will advance remote sensing, orbiting, landing, and thermal drilling technologies, setting a precedent for exploring other icy moons and exoplanets. Our goal is to assess the habitability and potential for prebiotic life on Enceladus. TIGRE stands for Thermal Investigations of Geothermal Regions of Enceladus, paying homage to the planet's hydrothermal events and Tiger Stripe landforms. Our team of 8 is split into Team Gaia, responsible for the land distrust system, and Team Poseidon, responsible for the water sampling system. My name is King-Diorr Willsun, and I live in Minneapolis, Minnesota, and go to school at Phillips Exeter Academy.
Hi, my name is Cristian Diaz. I'm from Houston, Texas, and I go to Diaz Southeast.
I'm Rohan from Westwood High School in Austin, Texas.
Hi, my name is Nehemiah Chow. I'm from Austin, Texas, and I'm homeschooled.
Hi, my name is Khudorozhkova, and I live in Tumble, Texas, and I attend Tumble Star Academy.
My name is Prabhleen Kour, and I'm from Yuba City, California. I am from River Valley High School.
I am Collin Loeks, and I am from Powers Lake High School, North Dakota.
Hi, my name is Mihir Gannavarapu. I'm from Katy, Texas, and I go to Jordan High School.
This is our mission patch. The centerpiece of the mission is Enceladus, and its parent planet, Saturn, is displayed in the background. The 4 tiger stripes that we plan to study are overlaid on top of the moon. Inside one of the tiger stripes is a cross-section of Enceladus to display the icy crust and subsurface ocean that we plan to study in our mission. The mission name, TIGRE, or Thermal Investigations of Geothermal Regions of Enceladus, is boldly displayed across the center of the patch. The border colors also reflect the same theme as the cross-section, where there's an icy blue exterior and a dark blue interior. Each of the last names of our team members are displayed on the exterior layer of the patch.
Enceladus has emerged as a compelling destination due to a confluence of factors. It has a subsurface ocean beneath its irregularly thin ice crust on its south pole. In the ocean, there's a high possibility to study potential extraterrestrial life. During a flyby through the ejected plumes from geysers, the Cassini spacecraft collected samples of the dust and ice from the plumes and detected the presence of CHOMPS elements. The presence of these elements have elevated this moon to the forefront of astrobiological research. CHOMPS elements are fundamental building blocks of life, and their presence significantly enhances the possibility of biochemical processes occurring. In the South Pole, there's an active area called the Tiger Stripes. These Tiger Stripes consist of 4 subparallel linear depressions that allow the subsurface ocean to exit, making geysers. These geysers constantly shoot water at high speeds out of the exosphere where it freezes and falls back down to the surface. The exact cause of the formation of this feature is still unknown, but many speculate that there are hydrothermal vents on the ocean floor that cause these activities to exist. All these features make Enceladus a prime location for research and space studies.
Prior to planning specifics of our mission, we outlined our mission's 3 main goals and their scientific importance. The first goal was to understand the structure and material composition of Enceladus's icy crust and subsurface ocean. This will help us locate any potential regions of interest based on surface or geothermal features, plan future landing sites based on the ice depth and geyser locations, and gauge the stability of any potential habitable zones in the ocean. We also want to search for indicators of habitability, life forms, and unique chemical composites. This would provide us with an understanding of the potential habitability of Enceladus. Moreover, it is crucial for us to detect CHOMPS, the fundamental building blocks of life, as well as any potential organic or inorganic compounds that might suggest the presence of prehistoric microbial life. Lastly, we aim to collect information for future missions into icy moons. This will be done through analyzing the results of how our drilling system and sampling system move through the crust and subsurface ocean of Enceladus. Moreover, we will be able to learn about placing an orbiter in Saturn's rings, which could help for an exploration to other Saturnian moons such as Titan.
For our brainstorming process, each of our team members came up with unique ideas to accomplish the 3 goals of the mission. Each member researched Enceladus through NASA treks and previous mission designs to generate ideas of components that would be logical and optimal for our mission.
3 ideas were created by each team member, and each idea was critiqued by the 3 members of the sub-team. Some ideas included orbiter satellites as well as AUVs. Then each member used a constructive criticism received from others to create a final idea sketch individually. Sub-teams combined the individual ideas to come up with a theoretically sound and plausible final design, which was used as a basis during the building process. Within the sub-team discussions, we were able to overcome multiple pseudo-restraints that individual ideas had by taking the best aspects of multiple designs into account. Ultimately, our 2 sub-teams, Team Poseidon and Team Gaia, created a visual display of the final design while continuing to research materials, geological aspects of the mission, and improve the design over time.
During the prototype phase, Team Poseidon honed in on the challenge of reaching the subsurface ocean and collecting water samples. We engineered a sophisticated thermal drill design inspired by previous cryobot designs such as Archimedes or Recos. After making this design, we decided to create a prototype of the water sampling system that would fit the constraints of our drill.
Team Gaia decided to focus on the task of landing on the surface of Enceladus. During the preliminary stages, the instruments required for accomplishing the goals of sampling falling ice, as well as the packaging and deployment mechanism of the drill, were used to design a detailed lander. Through discussion, we reached the conclusion to prototype the thruster system of the lander and test the use of angled thruster mounts for minimizing horizontal velocity when landing on a low-grip surface such as the ice on Enceladus. The goal of the prototype was to simulate a real landing scenario by mimicking thrust in Enceladus' low-gravity environment, which is 1/100th of Earth. We intended for the propulsive lander to help us simulate the lack of an atmosphere on Enceladus and further our knowledge of the mechanisms required to land on the surface of Enceladus.
Next, in our subteams, we began building and constructing our prototype. A wide plethora of tools and methods were used to build the various ideas we had designed. To build the physical prototypes, each subteam went through an intricate and tedious build process. Nevertheless, each member's collaborative efforts and technical skills were used throughout the 2 weeks to build all of the mechanisms needed for testing our designs. Both subteams had to make a multitude of edits to the prototype through the building process to ensure that it was best suited for our mission.
The team began the building process by creating drawings of our water sampler. We each researched various designs of water samplers to see which mechanism was best suited for how we were collecting samples. From there, we came together as a group, created the design we thought best, and sketched it out. This drawing was then translated onto a 3D computer-aided design file. Based on the design, we compiled a parts list for our sampler, and once we had our materials, the build began. We started with making the housing for the sampler, then we added the pipes to hold the water. Next, we added tubing to the pipes and a water pump with its electronics. While we coated the electronics, we added a watertight seal around any materials that touched water. Once all the components were coated, we created a 2.5-minute activation timer, during which we had to put circuitry into the pump and get it into the testing environment.
Our testing process, in contrast to our building process, was a much shorter ordeal, which consisted of only 3 trials of an automated water pumping period. Upon the completion of the previously mentioned 2.5-minute activation timer, a 12-volt diaphragm water pump, operated by an H-bridge motor driver, filled up our 3 storage valves with water during a 25-second pumping period. All the while, a simulated gaseous sample analysis was performed by telemetry that recorded temperature and humidity, DHT11. Side movements were recorded by an accelerometer and gyrometer, the GY521, which respectively reported acceleration, rotation, and more temperature data. An OV7670 camera, GSN SR4T, and HC06 Bluetooth module were additionally planned to process visual data, emit sonar signals underwater, and allow remote terminal operation. However, time limitations prevented their addition, and the components were not necessary.
Next, Team Gaia began by identifying the parts required for the lander as well as the timeline of construction. We began by identifying the sensors and electronics required to move and control the lander, using the ultrasonic sensor to sense the distance between the ground and the lander, as well as the gyroscope for orientation control. This would allow us to control thrust based on the altitude at an individual motor level. We decided to use an Arduino Mega as well as the IDE software to regulate thrust and manage orientation as well as altitude. We soldered each of the 4 motors to their respective speed controllers and wired the controllers in series to our Arduino. We made use of a separate breadboard to expand our ground wires for using the gyro and ultrasonic sensor. Next, we made use of wooden dowels and 3D printed components when connecting the 4 load-bearing legs, which would house the legs for the lander as well, to spread the force of deceleration across the lander and be able to support the instrument suite as well as the drill deployment mechanism that would be on top. We tested our lander in 3 separate stages, including power delivery, thrust, and automated distance measurement. This allowed us to test each aspect of the drop in a controlled manner without having to actually test the drop, which might present some other variables.
Designating materials for future missions is complex, so we chose to use proven materials from previous missions. Although these may be replaced by future innovations, we use current concepts sparingly. Our design priorities were materials resistant to extreme cold, negative 200 degrees Celsius, and radiation. Suitable materials already in use on spacecraft include aluminum alloys for their strength and lightness, titanium alloys for durability and performance in code, reinforced carbon polymers for lightweight structure, and multi-layer insulation for radiation protection. Alternative materials like aerogel show promise, their full utilization has yet to be realized, and with the travel towards Enceladus taking years, questionable materials aren't ideal.
At this point of the mission, the subteams reconvened into one group and began combining the 2 separate ideas. We made the overall plan of the mission from the orbit to the drilling.
Our mission consists of three main components: the orbiter, lander, and drill. Our orbiter will stay in orbit for 2 years, and during these 2 years, the orbiter will collect an assortment of valuable data. Among the data will be a detailed map of the surface of Enceladus. This is vital to the second component of the mission, the lander. With this detailed map, we will finalize our landing location in the South Pole near an active geyser and send down our lander. The lander will hold all our instruments, which will be used to get data and analyze data from our surroundings and samples. Additionally, our lander will also be housing the third component of the mission, the drill. This drill will dig through 5 kilometers of ice to reach the subsurface ocean, where it will gather samples and then proceed to bring them back up to the lander for analyzing.
The orbiter would perform multiple flybys, getting gravitational assist for getting to Enceladus. As Saturn's natural satellite is located within Saturnian rings, the orbiter would take on a period 3 halo-shaped orbit, as a safety precaution and ability to conduct more detailed observations. The satellite would go around the moon with an average velocity of 250 meters per second. The orbit would be focused on the first liberation point, as it would provide more stability and safe fuel. Also, choosing to go around at this equilibrium point would provide us with a closer look of the South Pole. More specifically, the ground tracks of the orbiter would go straight through the TIGRE stripes. Now that we have talked about the orbit, let's transition into our actual orbiter's design. It is heavily influenced by 2 Earth satellites, ISAT-2 and GRACE. The spacecraft will be powered by gallium arsenide solar panels that ensure that it is light, sturdy, and sufficiently powered. The orbiter would receive the signals from the lander and send them to Earth either directly or by bouncing them off of Mars Renaissance orbiter in case of an obstacle blocking the path. The orbiter would carry the radar for icy moon exploration to track the thickness of ice, a thermal infrared scanner that will create a temperature distribution map, a high-resolution camera high-rise to take pictures of the surface, and a gravimeter would measure the fluctuating gravitational pull. Through the collected data, the orbiter would be able to choose the exact location where the lander will reach the surface.
The landing location needed to be a place that did not have rapid changes in elevations that could cause damage to the lander upon landing. Furthermore, we decided not to land directly on a tiger stripe or geyser, but rather land close to them to be able to fulfill our goals without being directly on top of the high-speed geyser debris. Since the thermal drill will be deployed directly from the lander, and our dust collector will also be from the lander, our optimal location must still be in close proximity to a geyser. Finally, we wanted the point to have a low surface elevation so that the drilling distance is minimized. Based on these points, we decided that the lander will land within 5 kilometers of the region bounded by the coordinates, with a latitude of approximately -83 and a longitude of about 321 on the Baghdad stripe, which is the second stripe from the left shown here. This location has an elevation of -450 meters relative to surface level and a geyser within 6.4 kilometers of the center of the landing zone labeled on the dotted line in the image.
The lander will house our drill, sampling devices, sample analyzers, and will be powered by our RTG. It will be made with metals, composites, and insulation materials, all of which will be extremely tolerant to radiation and cold temperatures. Enceladus has no atmosphere, so thrusters will be used to guide our lander and slow down our descent to our selected location. Once on the surface, the lander will have a system to anchor itself into the ice and start recording data about its surroundings using a Mastcam Z. The camera will allow us to send high-quality panoramic photos back to Earth. We will then proceed to take the samples of our surroundings with our ice and dust collector. The collector will be shaped like a funnel and will be able to catch the ice being expelled from the geysers and the interstellar dust that falls with the ice from space. The dust will be sent through a dust analyzer in the lander, and the ice will be sent through our sample analyzer process for analyzing. Our sample analyzer process will be using an assortment of instruments to give us a detailed idea of what elements, molecules, and chomps exist on Enceladus. All the data gained will be sent back to Earth, and we will be able to have a detailed idea on what exists on Enceladus.
Our final drill design utilized a myriad of different components to ensure that we are able to effectively get in and out of the icy crust with our collected water samples. Starting from the bottom, we have our lower drill. This drill utilizes the direct laser penetration technology aboard the Archimedes drill to create a highly concentrated thermal beam and melt through the ice, as well as mechanical drilling to form an initial divot. Above is a temperature sensor, followed by the next major component, which is the water sampling system we discussed previously. Moving up from the water sampler is a large wiring section, followed by a sensor complex. We then have a movement system that controls precise transitions in the XY plane and the small plutonium oxide RTG for powering our drill. Finally, after the tension and load sensors, we reach the upper melting tip. This is a heat-based drill that will be used for sample recovery by drilling upwards and heating the tether it is attached to so it is able to move. To understand the functionality and feasibility of our design, we created the table on the left to analyze metrics such as energies, masses, analysis targets, and outputs of the instruments aboard the orbiter, lander, and drill. We can see that the scientific payload is relatively inexpensive to power and move. The shortened Science Traceability Matrix, or STM, on the right is used to show how each instrument answers a specific part of the mission objectives and to show that every instrument contributes to completing our mission. The elements are as follows: radar for icy moons, RIME, high resolution mass spectrometer, HRMS, thermal infrared scanner, TIRS, GRACE gravimeter, high resolution imaging science experiment, HiRISE, MASTCAM Z, quadruple mass spectrometer, QMS, gas chromatography mass spectrometer, GCMS, microscope, nanopore, electrochemical sensor array, ESA, and finally an alpha particle X-ray spectrometer, or APXS.
During the mission, we encountered multiple challenges, but we were able to identify methods that could successfully investigate icy moons. At the same time, we designed our mission in ways that could be the foundation for future exploration, understanding, and observation of Enceladus.
Some challenges we foresee in the future are communication with Earth due to the distance between Enceladus and Earth, radiation damaging to our instruments, and the extremely frigid temperatures of Enceladus's icy crust and subsurface ocean. Landing on the icy surface of Enceladus also brings the challenge of no atmosphere. Our greatest challenges were regarding power and minimizing the uses of RTGs alongside engineering a method to collect water samples that is reliable and recoverable.
For future missions, developing an alternative method to power the satellite that does not rely on solar energy is crucial. As the south pole of Enceladus enters the fall season, the area would be submerging into darkness. Further advancements of the sustainable power systems that can be utilized beyond the Jovian system would provide us with a longer living mission that would be able to still be active during the dark periods. Also, continued technological developments should take place to design a mechanism to go further down in the ocean. Exploring the depth of the ocean would provide us a more detailed composition of the water, as liquid closer to the surface loses some of its chemistry. Lastly, we believe that in the future missions, mapping the core of Enceladus should be prioritized, because the irregularly shaped core could hold the answers to the activity happening on the South Pole.
The proposed mission to Enceladus, TIGRE, offers significant scientific benefits by advancing our understanding of Saturn's intriguing moon. By studying its surface material and subsurface ocean, TIGRE aims to assess Enceladus's habitability and potential for prebiotic life. Data from the lander's sampling devices, thermal drill, and orbiter remote sensing will provide comprehensive insights to the composition and formation of Enceladus's subsurface oceans. These findings could also inform our understanding of other icy moons, broadening knowledge of potentially habitable environments in the outer solar system. This mission will advance remote sensing, orbiting, landing, and thermal drilling technologies, setting a precedent for future exploration. Overall, TIGRE ensures a thorough investigation of Enceladus's potential to support life, contributing valuable data for future missions and enhancing our understanding of astrobiology and planetary science.
During the short 2-week period at SEAS, I have learned many wonderful things. SEAS has been pivotal in my ability to work with a team to teach and be taught different skills like coding, soldering, CAD, and the engineering process. I can confidently say that SEAS has been a life-changing experience for me.
Although not proficient by any means or starts with definition, I can confidently state SEA's program's greatest effect on me was increased knowledge and perspective for other specialties of STEM such as coding and wiring. The presence of various teammates have undoubtedly served as beacons of new perspectives, which have already reignited my passion and secured my passion for STEM as a whole.
In only 2 weeks, the SEAS program has been instrumental to augmenting my technical and collaborative skills. Working within a team, conducting intensive research, and building a mission from scratch with Arduinos, CAD, and PCB gave my programming skills a platform to be authentically and impactfully leveraged. My teammates have only further stunned me with their ingenuity and skillful implementation of their talents, and our mentor has been a spark of joy in our everyday lives.
I am very grateful for my time with the SEAS program because I got to meet so many people with the same interest as me, as well as conduct genuine research, which only elevated my interest in entering the STEM field.
I have had a wonderful time at SEAS. Being able to work with mentors who are actively in the industry and hearing from astronauts has truly inspired me to continue to pursue a career in aerospace. Additionally, working with other interns and researching about our mission has sharpened my STEM skills and has also taught me new skills. I will forever be grateful for this opportunity, and I hope to continue to work with y'all in the near future. Thank you.
SEAS has been truly a life-changing program. I'm confident to say that SEAS has changed my view for my future for the better. I'm so beyond grateful for this amazing opportunity, and I have learned so much about NASA and working on missions. Thank you so much.
The SEAS program has taught me a lot about collaboration on an engineering project. Going through the entire design process of the team and picking up skills along the way has made SEAS an incredibly beneficial experience that will go on to aid me in my future endeavors.
The SEAS program has been a transformative experience, enhancing my technical skills and teamwork through hands-on projects involving coding, CAD, and mission design. Learning from industry mentors and collaborating with peers who are passionate and proficient in a variety of fields has inspired me to pursue a career in aerospace and STEM, leaving me grateful and more prepared for my future endeavors.
We've been fortunate to meet multiple experts to consult for our mission. Dr. Leonard, a member of Planetary Geosciences at the NASA Jet Propulsion Laboratory, JPL, advised us on the geological factors of Enceladus. She advised us with important information on selecting a landing site. Professor Adam Loeks is a lecturer at UT Austin. With his realistic approach to our mission, he guided us to act within reason and proposed a few resources for us to use. Lastly, but certainly not least, we also consulted with Brian Day over a Zoom meeting concerning NASA treks and planetary imaging. Day works with NASA in the planetary sciences.
Thank you!